Hello there, Algebra students. This is Mr. Kashi speaking. With this video, what we're going to be doing is going through the notes and the examples from our section on 3.2, which is getting into functions. Hopefully you've already done your warm-up problems and your 3.2 vocab. The two vocab terms today were function and function notation, and we'll obviously be talking about those throughout these slides as well. So last time we talked about relations and how x's and y's are related, and now what we're going to do is we're going to be classifying those relations to determine whether they're functions or not. So the first main thing that you can see is called the vertical line test, and that's a simple test that you can do to a relations graph to see if it's a function or not. And basically it says if any vertical line passes through the graph more than once, the relation is not a function. So if it passes the vertical line test, it means that it is a function. If it fails, by meaning that it crosses more than one point, it would not be a function. So like go through here. If relation number one is just a line, okay, and you can follow along if you'd like. Okay, that vertical line is only going to cross that line once. Okay. Relation 2, this is what we're going to be talking about more in second semester, is called a parabola. If you were to slide that green vertical line back and forth, it would only cross that relation once, cross that green line once, so that would be a function as well. Over here, don't really need to know what the equation is, but obviously you can see that it's a circle, and that circle crosses the vertical line twice. So since it crosses that green vertical line in two spots, that means it's not a function. So moving on to the 3 down here at the bottom, this is another line, relation 4, another line there, so that would be a function as well. Here, this looks like kind of like relation 2, but it's put on its side. So obviously it crosses that vertical line twice, which means that it's not a function because of those 2 points crossing the graph there. And then finally, for relation 7, here, I know we skipped 6, but that's all right. Those are the ones that we were going to be talking about. This would be a function. If you were to slide that green line left and right, it would still only cross the graph once, so that would be a function as well. So other ways of determining function, just basic definition of function is a relation in which each element of the domain is paired with exactly one element of the range. So each x needs to have a y. And not only does each x need to have a y, it can only have one y. That's the main point. So there's different ways of looking at relations. So this first one is just a mapping of a relation. And because each x has exactly one y, that would make that a function. And then if you're to take a look at this graph here, it kind of has this bend here. But if you were to think of putting a vertical line, just like on our last slide, sliding that vertical line back and forth, it would only cross that vertical line once. And so that means it would pass the vertical line test, and we would say that that is a function. The vertical line test is just a visual way of talking about how every x has exactly one y. So taking a look at this mapping down here, each of these x's in the domain has exactly one y. Now, I understand that -2 and 2 both go to 3, but that still is under the definition of our function. Each x has exactly one y. Moving on to the table here, we have an x that has, in our domain 2, has a relation of 3, and then 2 that has a -3. So because of that, that would not be a function, because we have an x that has 2 different y's, which would fail the vertical line test as well if you were to graph that type of a relation. And here as well, we have the 4's, the x's that are in our domains go to 2 different y's. Okay, so that would not be a function as well, because the 4 here goes to the 7, and the 4 here goes to the 13, which is against the definition of what a function would be. Every x has to have exactly one y. In this case, in these last two cases, they have two different y's. Right? Going through these, determining whether these are functions or not. If you could pause the video and just take a moment or two to decide whether you think these two, A and B, are functions or not. Then now we'll go ahead and go on here. So for A, we would say that this is not a function because we have this 3 that has basically these two. As soon as it goes out in two different directions in a mapping, that means that we do not have a function. And that's the easy way of telling when we have a mapping is we should only have one arrow leaving each of the elements in our domain. So as soon as that 3 was going to point to two different elements in our range, we already knew it was not going to be a function. And here, each of our domain elements only has one arrow going to the out. I don't really even need to look at the range. I can just see that there's one arrow leaving each of our x's. Does not matter where they end up over here, but as long as there's just one arrow leaving each element in our domain, that determines that we have a function. Right, so going on to kind of an example, we have some data here of some teams doing the long jump. And so here it says find the domain and range of this relation. Make a table to determine if the relation is a function. Okay, and so here we have our domain would be the teams. In this case, it would be 1, 2, 3, 4, and 5. And then the range would be the distances that they have. And it would be 20.6, 21.5, 20.9, 19.4, and 20.2. Now I know it says to make a table, determine whether it's the relation is a function or not. What I'm going to do is instead of drawing a whole table down below, I'm just going to mark the domains. I kind of lined them up here on purpose that team 1 was 20.6 and team 2 is 21.5 and 3 and 4 and 5. So here you can see that each of the x's have exactly one y, which that would be the situation that we're in. There wouldn't be a way for a team to have two different results in this competition. So moving on here to another idea, it's called function notation. And really function notation is just a different way of writing equations to talk about once we start evaluating them. So an equation would look like this, and then we can just take that y and turn it into what we call f of x. And there's many different reasons why we use function notation, especially getting into calculus and things like that. So it's just preparing you for those function notations. And so here, if we were to say f of x equals negative 2x plus 9, and then they were to say f of 4, what that means, f of 4, is you can see here where x was, now we've replaced it with a 4, and that's what we're going to do in our equation. Wherever we see an x, we're going to put a 4. So in this case, we're going to plug in a 4 for x, right? So where it used to be x, now is 4. And now we just have to simplify. So negative 2 times 4 would be negative 8. Right there. Bring the 9 down. And negative 8 plus 9 would equal 1. So our f of 4 would end up equaling 1. So that 4 is just really saying, hey, we're going to plug that 4 in wherever we see an x in the equation. So moving down here, we have f of 4 plus 3, which if we had already done f of 4, we could just add the 3 there and get 4. But if we had to start from scratch, what we would need to do is we need to go through and plug the 4 in, do the negative 2 times 4 and get 8 plus 9. And then we have this plus 3 out here as well. And then you can see how the negative 8 plus 12 can simplify down to the 4 that we should have gotten anyways. So if you already did the f of 4 equals 1, you could just do the plus 3. So 1 plus 3 gives you 4. So that would have been a faster way, but if you had to start from scratch, you'd have to simplify what we did in that first 2 steps there. Now we have an interesting example here where we have f of 5 minus f of 1. So we're really going to be using this equation twice. We're going to be plugging in 5, the first one, and then we're going to be plugging in 1 for the next. And what I want to make sure that you know is that you need to use parentheses here. It's very important that you use parentheses in this example. So I know this looks like a lot, but I'm just rewriting the f of 5 minus f of 1 all the way down here. So here we have the first one where we have negative 2 times 5 plus 9. So we plugged in the 5 right here for x. And then we're subtracting f of 1. So we took that 1 and we're plugging that in here for x. And notice how we put parentheses around the second one. We're subtracting both of these here. So we have negative 10. So the negative 2 times 5 simplifies down to negative 10. And then just multiply the negative 2 times 1 here. Here we have negative 10 plus 9. So this simplifies down to negative 1. And then we have the negative 2 plus 9 simplifies down to 7. And we have negative 1 minus 7, which gets us our answer of negative 8. Go ahead and pause the video if you need to take more notes on that example, but I am going to scroll up here and go to our next function. So here we have g of x equals x squared plus 3x minus 6. And this function notation is now saying that we have g of 3. So we're going to plug that 3 in for both. Wherever we see an x, we're going to plug in that 3 in for both. So when we do that, we're going to have 3 squared plus 3 times 3, and then we have that minus 6 at the end. So 3 squared obviously it gets us the 9, and 3 times 3 also gets us 9. And then we can simplify that down to the 18, and the 18 minus 6 will give us our final answer of 12. So really just practicing function notation, and it's telling us what to plug in for x, which is just a easier, simpler way to get that evaluated. All right, our last slide here goes through a financial literacy problem. So Macy had an initial deposit of $250 into a bank account, and each month she deposits the $80 into the account. Assuming there's no interest, which it's important, the function f of x equals 80x plus 25 represents the total amount of money she will have in the account after x months. And then what we're doing is we are trying to find out, we're plugging in 9, which means that we want to know how much money we're going to how much money we're going to have in the account after 9 months. So we're plugging that 9 in for x right there. And after we do that, we have the 80 times 9, and then we have the plus 250. So 80 times 9, if you need a calculator, or 8 times 9, 72, and then just add the 0. That would be 720 plus 250, and that would give us the 970. And technically, if you're answering the problem, that would be $970 in the account after 9 months. And that's what this is meaning, is saying after 9 months, the total of money in the account is going to be $970. So hopefully, if you haven't already, you need to pause it and go back and maybe jot down some notes. Feel free to do that, and I will be helping anybody that has questions on any of the examples that we just went through in class.